All right, today we're going to dive deep, I mean really deep, into the microscopic world inside your favorite gadgets. We're going to uncover this hidden battle that costs energy, creates heat, and actually sets the ultimate speed limit on our technology.
I mean, you've felt it, right? Your phone, your laptop, even your charger, after you use them for a bit, they all get a little warm. We just kind of accept it as normal. But have you ever really stopped to ask, why? What is actually making that heat?
Well, that warmth you feel, it's basically the collateral damage from this incredibly fast, high-stakes conflict. It's happening inside these microscopic little things called transistors, which are basically just tiny, tiny electronic switches. So let's take a closer look, shall we?
Okay, so to really get a handle on this problem, we first need to talk about the difference between how we wish a switch would work, in a perfect world, and how they actually work in our world.
So in a perfect world, a perfect theoretical world, right? An ideal switch would be instantaneous. Bam, on, bam, off. No time in between, and absolutely zero energy lost. But, we don't live in a perfect world. We live in the real world. And here we use practical switches, and that really just means the tiny transistors that are the building blocks of, well, everything. And these real-world switches, they take a tiny but very real amount of time to flip from on to off. And believe it or not, that tiny little delay, that's where all the trouble starts.
See, that little moment of transition, that fraction of a second when it's going from on to off or off to on, well, it's not free. It has a cost. And in the world of electronics, that cost has a name: switching loss. So here's the absolute heart of the issue. Think about it. When a switch is fully on, current is flowing, but there's almost no voltage across it. When it's fully off, there's voltage, but no current is flowing. In both of those states, fully on or fully off, very little energy is actually wasted as heat. But what about that tiny little moment in between? That's when you get this overlap, where for a split second, you have both voltage across the switch and current flowing through it at the same time. And that, my friends, is when things get expensive, energy-wise. And this quote really just nails it. It's from the source lecture, and it says it all. The switch current and the switch voltage will have some overlap, so we will have some switching loss. It's that simple and that profound. That overlap, that moment when the two cross paths, that is the moment energy gets lost. It just turns directly into heat. Now, don't worry, the math here is actually pretty simple. The energy you lose in just one single flip of the switch, it's basically the voltage times the current times the amount of time that overlap happens. And yeah, for one switch, that's a teeny tiny amount of energy. But here's the kicker. The total power you lose is that tiny little bit of energy multiplied by the switching frequency. That's how many times per second this whole thing is happening. And let me tell you, that adds up incredibly fast. So, okay, we're losing a little bit of energy as heat. You might be thinking, what's the big deal? It doesn't sound like a total catastrophe, right? Well, it turns out this tiny, seemingly insignificant loss is actually one of the biggest roadblocks in all of modern electronics. And that's a totally fair question to ask. I mean, a microscopic energy leak inside one tiny transistor, how on earth does that affect the phone in your hand or the laptop on your desk? Well, the implications they're just massive.
Yeah, this is about way more than just wasting a little bit of battery. This tiny loss has enormous consequences. For one, it puts a hard speed limit on how fast our devices can actually run. It's also one of the biggest things stopping us from making them even smaller. And in a worst-case scenario, all that heat can build up and literally just destroy the switch.
And remember that frequency part of the equation we just talked about? Get this. In a modern power converter, like the little brick that charges your laptop, these switches are flipping on and off over 100,000 times every single second. At that kind of speed, all those tiny little losses, they turn into a massive, constant river of wasted energy and heat. So the big question is, how do we fix this? How do we deal with this problem? Well, engineers, being the clever people they are, came up with a really elegant solution. It's called a snubber circuit. The best way to think of a snubber is like a personal bodyguard for the main switch, the transistor. It's this small secondary circuit, and its entire job, its only job, is to jump in during that stressful transition period, take the hit, absorb that energy spike, and protect the main switch from getting fried. So this little bodyguard circuit has two main jobs. Job number 1, keep the switch inside its safe operating area. You can think of that as the zone where it can work without, blowing itself up. And job number 2 is to reduce the amount of energy that's lost as heat right inside the switch itself, which is the most delicate part. Now, what's really interesting is that the problems you face when turning a switch on are actually different from the problems you face turning it off. So, naturally, engineers came up with different strategies for each part of the process. And this really breaks down the 2 main game plans. When you're turning the switch off, the snubber will often use a capacitor. You can think of a capacitor as like a tiny, super fast charging battery. It just gives the current a safe place to go for a split second. Then, for turning the switch on, the strategy is different. The snubber might use an inductor, which acts kind of like a speed bump for electricity, just holding the current back for a moment. But in both cases, the goal is exactly the same: prevent that voltage and current from overlapping.
But, and this is a really big but, this solution isn't free. There's always a trade-off in engineering. The snubber does a great job saving the switch by grabbing all that dangerous energy, but that energy has to go somewhere. It doesn't just disappear. The snubber circuit itself now has to deal with it, and usually that means turning it into heat. And this quote is just fantastic because it gets to the heart of this trade-off. It says, "The total energy we lost may be even more, but we want to do this because we want to keep the switch safe." I mean, think about that. You might actually be making the whole circuit less efficient by adding this part. So why on earth would you do it? Well, because the number one goal isn't always pure efficiency. Sometimes it's about reliability. It's about protecting the most important, most vulnerable part of the system. And really, that's the big takeaway here. Good engineering, great engineering, isn't always about chasing perfect, 100% efficiency. A lot of the time, it's about making smart, intentional trade-offs. And in this case, it means you're willing to waste a little more energy overall just to make absolutely sure the device works safely, works reliably, and doesn't cook itself from the inside out. So, the story of the snubber, it's just a perfect little window into all the hidden complexity and really clever problem solving that's happening just beneath the surface of all the tech we take for granted. It kind of makes you wonder, right? What other invisible battles are being fought and won millions of times a second just to make our modern world possible? Something to think about. Thanks for joining me.